Because I'm tired and I'm actually sitting fairly upright, I'll probably just sit here. What we're going to do today is go back to the ester lab and try and determine its equilibrium constant for that overall reaction. Right? The calculations are a bit messy on it, and you will have a lot of repetitive calculations, but they are, unfortunately, in my opinion, are not repetitive enough to make Excel worthwhile using. So you're going to end up doing a sequence of at least 5 calculations pretty much again and again and again. And each of those full calculations, I would recommend you spend doing it on a page, a full page. Okay? So that way all of your results and calculations are kind of neatly, succinctly put together, so that if anything goes wrong, I can help you find out where something went wrong and we can fix that mistake. Okay? That is up to you, though. As far as the report goes, as far as your calculations, we will talk about that. It's a bad idea. Towards the end of this recitation, the only calculation I would need to see would be all the calculations necessary for trial 5, which is the more complicated calculation, which is why that's the only one I want to see. Because I kind of figure if you can do trial 5, you can do all the other equilibrium trials. Okay. As far as this report goes, title as always, then an abstract, then your methods, and then your results and calculations. Okay. So it's not too bad of a report as far as assignments goes, because you don't have to write the introduction, and that's usually the worst of it. Okay. In the title, what important things do you think should show up in the title? What's that? Yeah, so what keywords? Equilibrium constant. What else? Esters smell nice would be the introduction. The title having ester would be good, yes. We can be a little bit more specific with the ester. Not a bad idea to mention hydrolysis. I probably wouldn't, though, because it's more effort. It's more on the organic side of it, and we aren't looking at that side of it. What else can you tell me about the ester? It's kind of an odd question, because you all are going to be like, well, I don't know anything about the ester. That is something that you could tell me about the ester in your unknown, or in your title. So you're looking for an equilibrium constant for an unknown ester. You don't know what it is. Yeah?
Sorry, I just realized I took somebody's notes for the KA lab. Yeah, if anyone doesn't have their notes, that's hard something.
No worries. Unknown ester, we are doing a reaction of making that unknown ester, and that's where you could go into with hydrolysis if you wanted to look at it in that respect. I would just say a reaction of an ester. Last big piece that should show up. Is it just the esterification? So it's just the ester, the carboxylic acid, the alcohol, and water. Those are the only things that show up. Right? It's acid. What's the role of that acid? Not quite. It's actually a reactant. It's a catalyst. Okay? So it's acid catalyzed. So as far as ideas that should show up in your title, we've got the equilibrium constant, your ester, ideally that it's an unknown ester. We're looking at the reaction with that ester, and then it's an acid catalyzed reaction. Okay? So you should somehow combine all of those ideas into a coherent title, and you've got your title pretty much set up. What would show up in your abstract? Results, really important. What should show up even before the results? The goal. What is your goal for this experiment? Find the equilibrium constant for the ester reaction. So you should write out the general format for that reaction. How are you determining it? So we could mention the acid catalyst that's helping the reaction, but that doesn't allow us to determine the equilibrium constant. We are titrating with a standardized base. Okay, so that would be your one-sentence summary of both a goal and potentially even your method section, if you can incorporate titration with a base. Then we could bring in the results. What would your result be? That would be your discussion-ish aspect of it. What's the actual result? Equilibrium constant. Okay. You should include a standard deviation on your equilibrium constant. You will report the average with the standard deviation. Okay. I'll show you how to get Excel to do the standard deviation for you, and then that way I don't have to teach you how to do a standard deviation. And that will give you an idea of the error as far as your calculation goes. Okay. After all of that, we could then say whether our result was good or not. We don't have anything to compare to, but we do have the standard deviation. So you could say the standard deviation was small. So you could say it was good because that worked. The very last thing, success. Statement of success. Was it a good experiment, or was it a successful experiment or not? Okay. Make sure you provide some explanation for why. Okay. You then go into the methods section. Again, you haven't seen any feedback yet on methods, but there is example method sections posted to Canvas. I do recommend you read through those, particularly before you turn in the KA lab, okay, at least officially. If you would like help with the method section, write one up, submit it to me, and I will go through and tell you why you said too much. And probably delete half of it, okay? And then you can go through and do the results and calculations, okay? Questions about any of that straight off? Okay. As far as general introduction material, again, we don't have an introduction and we don't have to write a discussion and conclusion for this. So it's not too big of a deal as far as this information, but it's nice for you guys to realize what's going on with it. Why do we determine the equilibrium constant? Okay. If we have a big equilibrium constant, what does that mean? What is an equilibrium constant? How would we solve for it? If we have a big equilibrium constant, what does that mean? We get more products out of our reaction. Okay. What we'll end up adding to that is then a feasibility of the reaction when we move into the thermodynamics chapter. Okay. So it gives us an idea of whether or not that reaction is something that's going to generate products to any reasonable extent or not. Okay. If it's a reaction that doesn't give us any products to any large amount, we aren't going to do that reaction because it's not going to give us the results that we want. Okay? So if we can get an idea of the equilibrium constant, that can help us decide whether or not it's a good idea to do that experiment or not. Okay? If we then take it a step further and compared different ester reactions and looked at the equilibrium constants for each of those individual reactions, we could start to draw parallels between them. How does the structure of the alcohol and the acid affect the equilibrium constant? So if we make the structure larger, do we get more product? Do we get less product? That allows us to interpret how the reaction is going to work. It can give us more information. We can extrapolate to other things. Okay? So determining the equilibrium constant is kind of a big deal. Okay? Other things that we would include in the introduction, an overall reaction, and we'd also want to mention that it's acid catalyzed. Okay? Because we are using that acid catalyst. How are we going to end up determining it? Well, we need to know the concentration of our products and reactants. To get those concentrations, we have to design an experiment to allow us to determine those. Because we can't monitor most of the concentrations of those species, what we're going to have to do is look for something to evaluate. So if we look at our overall reaction, what did we start with? I forget. We started, the equilibrium we're doing is alcohol plus our acid, right? That was a question. Is that correct? Yeah. Okay. So what we want to be able to do is to figure out our equilibrium concentrations. We can figure out our initial concentration because we put them all there. But to get the equilibrium concentrations, we would have to monitor or determine those concentrations at a later date. Everything that we've done so far looks at a reaction that allows us to determine it. If we take a look at the functionality of an ester group, they're relatively non-reactive, which means I wouldn't be able to determine its concentration easily because it doesn't react with anything. We could try and look for color. Maybe its color is different. Turns out esters are mainly colorless, so we can't determine its equilibrium concentration. Alcohols, very similar issue. They do run lots of other reactions, but those reactions aren't going to be the easiest to work with. Okay? The one last thing that we've got in here is the presence of the carboxylic acid. Do we know any chemistry about carboxylic acids that we could take advantage of? Do we know any chemistry of acids that we could take advantage of? What do acids react with? Bases. So what we're going to do is try and determine the concentration of the acid. Once we know the concentration of that acid, we can then determine the concentrations of everything else, okay? Because we know this balanced equation, okay? To determine that concentration of acid, we need to make sure that we know how much base we're adding. So what we're going to go through and do is a titration, like every other experiment we've done this semester, with sodium hydroxide. So to do that, we need to know the concentration of the base we're adding. How would we determine the concentration? We standardize it just like we did with the last lab. So today's experiment is just to make your standardized base solution and then standardize it. Determine that molarity. Okay, that's your sole goal today, if you so choose. That, just like we looked at last week, is something that you can probably do in 30 to 45 minutes, and you'd be done. Okay? What are you going to do on the next day? We're going to do our titration against all of our ester mixtures. Okay? So we could start those titrations today. And in theory, you could finish the entire experiment today, just like you did with the last one. Okay? There are some limitations to that. Why did we not start this experiment right away last week? Why did we jump into the Ka experiment? This needed to get to equilibrium. If you do the entire experiment today, you are doing it 2 days early. In theory, it's possible that it's not at equilibrium. If it's not at equilibrium, what does that mean? All of your results are wrong. Okay? How important is that to you? More importantly, maybe, how important is that to me? I couldn't care less. Okay? So if you want to go through and titrate it all today, by all means, feel free to go ahead and do so. At very least, I'd titrate solutions 1 and 1A because there is no equilibrium in those. So we don't have to worry about those. Okay? So minimally today, standardization of your base. I would then add on top, titrate against solutions 1 and 1A. If you would like to, continue to go through and titrate the rest of your samples. That's up to you. Okay? And if you were writing a discussion and conclusion, you would then, are we writing a discussion and conclusion? If we were writing one, you could then go through and say why your results sucked because you didn't wait for it to get to equilibrium. Pretty simple. Okay? Question?
No.
There was a question. I thought there was a question. Okay. So, how we're going to go through and do this, once we determine that acid concentration, we can then go through a whole bunch of ice charts for each of our 4 ester trials. Okay? They are going to be messy. You've got all sorts of calculations that are tripping over each other to go into it. Okay? So it is not the most pleasant to deal with. We'll try and organize it as much as possible so you can get a feel for what you've got to do. Okay? Complications. We already talked about KHP, why we use KHP, why we use the phenolphthalein. Time we just addressed. If you start to titrate too early before it's reached equilibrium, then you're not determining the equilibrium constant. you'd be determining the pre-equilibrium not constant, so you'd be determining a completely useless value. Huh. Lucky you. One of our other big issues is going to be this water content. One of the reactants, or one of the products in the course of this reaction, is water. Right? So we would incorporate that into our equilibrium expression. Whereas in previous situations, we wouldn't include water because it's a liquid. Okay? So we would say its concentration holds constant. In the course of this reaction, it's going to hold pretty constant, but we still need to include it in our calculations, okay, for determining the equilibrium constant. So what we will do is come up with our K expression. We'll determine the concentration of our ester, the concentration of our water, and they will then divide by the concentration of our alcohol and our carboxylic acid. We will do that 4 times. The answer from all 4 trials should be close to the same number, okay, because it's the equilibrium constant. Okay? The other big issue, we do add water, so it does show up, okay, and we actually add water directly to our individual reaction. What else is an issue? When we added our acid catalyst, did we add just acid? No, we also added water. That water addition in the acid needs to be accounted for when we go through and determine the water concentration. Okay? So it's yet another step that we have to watch out for. I haven't done this calculation in a while, so it might get a little bit dicey when trying to organize it. We'll redo the calculations on Thursday after I've had a couple times to go through and do it to make sure that we get it nice and smooth. Okay? So today, minimally, standardize your base. We need to make an NaOH solution using solid NaOH, just like we did last week. Except the concentration of NaOH in this case is not 0.1. What's it supposed to be? 0.7. So how many or how much sodium hydroxide do we need to measure out? You all did the math. You get 14 grams, which is what I got. Previous semesters, I remember 40 number for being the number of pellets. I did a quick kind of comparison calculation, and I think it's closer to 80 pellets. If you would like to count out 40 to 80 pellets, by all means, go ahead and do that. I would recommend you just use the triple beam balances to get your 14 grams. Okay? I will try and go through and calibrate each of those, so all you've got to do is add the sodium hydroxide to the correct side of the balance and get your 14 grams. Okay? Then you will go through and titrate against your KHP to standardize. The procedure asks you to go through and again determine how much KHP to measure out. What is it? What was your pre-lab calculation? What was that?
You got 5.
I've heard of 5, which I can believe. Anybody else? Okay, about 5 grams. It's a lot of KHP. Remember last week you measured out, what was it, 0.4? Was it 0.4? Okay, it's a relatively small amount. You're doing 10 times that amount now. So it's a lot of KHP. Be aware of that when you go to measure it. Okay. What's the volume of sodium hydroxide you would be expected to use to titrate that against? If you go back to your pre-lab calculation, how did you get the 5 grams? Your pre-lab calculation should have started off with a volume of NaOH added. If you followed exactly like the lab procedure asked you to do, it was 35 milliliters. Because I know we can run a little bit tight on the amount of base in this lab, I actually backed it down and ran the calculation assuming 30 milliliters. So I would measure out closer to the 4.2 gram mark for KHP. Okay. That's optional, up to you. It's not going to change your results. but it will hopefully make sure that you've got enough of your base solution that you don't have to redo the entire experiment. Okay? If you start your titrations and you run out of base, what happens? You pretty much have to restart everything. And when I say everything, I mean everything. The ester solutions, everything. It's a mess. Okay? So be kind of careful with the amount of base you're using. Try to not overuse it. Usually we've got roughly 100 milliliters left over at the end. And worst case, I can sacrifice base from other groups and make your calculations even more convoluted than necessary, but it at least gets you to finish the lab. Okay? So be careful with what you're doing with your base. We don't want to use too much. Okay? You'll need to get the burette from the stockroom. Every partner should get a burette because you can go through the titrations faster if you do that. If you're working in a group of 2 or 3 for that matter, 4 standardizations for your titrations. Okay? 2 per partner. You can then go through and calculate the molarity of your NaOH solution, stash the NaOH solution in your drawer, and you're technically done for the day. Okay? If you would like to continue on, you are more than welcome to do so. Okay? So day 2, officially what we would do on Thursday, you'd get your burette again, and you'd now start titrating your standardized base solution against your 6 ester mixtures. Okay? Or however many left you've got. Okay? When you go through to transfer your mixtures into your Erlenmeyer flask for the titrations, make sure you rinse the beaker or your container with a little bit of water to get it all of it transferred into your Erlenmeyer flask. What's the issue with adding water? Water's part of our equilibrium expression. So what's the problem with doing that? It's potentially going to shift our equilibrium. What are we assuming? The equilibrium takes a long time to occur, which means adding a little bit of water right before you do the titration isn't going to shift the equilibrium enough to worry about. Okay? Because the equilibrium takes much, much longer to actually form. Okay? So when you go through to set that up, you will be rinsing with water. Don't worry about it. It's not going to affect your results. Okay? The rest of this is your calculations are a bit repetitive. I wouldn't say it's worth using Excel. If you want to set it up, I've had a few students go, oh, look, I can use Excel. I know you can use Excel to solve it. That doesn't mean it's easier to use Excel. Okay? As far as also organization, you'll notice at the top of these 2 slides, I've got partner 1 and partner 2. You could split it up that way. You guys both work together to get your base solution made. Then one partner work on the standardization titrations. The other partner work on titrating your ester solutions. That way you both end up doing roughly the same amount of work, and you'd get done relatively faster than if you broke it up individually. Okay? Kind of up to you how you want to do that. Yes?
For the KHP solution, it tells in 2 places to do 2 drops of phenolphthalein. Just 1 dose of the 2 drops. Like on 6 and 7 it says 2 drops.
As in I didn't say add phenolphthalein? Or?
No, it says in 2 separate places to do 2 drops of phenolphthalein.
Oh.
It says that's why it's
just saying do it.
4.
No, it doesn't matter. Phenolphthaleine's there just as an indicator. So, as long as you don't dump it in there, it's not going to affect your pH titration or your titration enough to make it matter. So, all you need is a few drops. Okay. Questions about what you're doing in lab? Okay. As far as the calculations go, what I would expect is to begin with table 1. Your individual trials and the molarities calculated from those trials. You can add some more information in there like the mass of KHP used per trial. I won't stress about that. Just tell me what trial it was and what your calculated molarity was. Then also give me the average molarity in that table. Okay? Sorry. As far as your calculations go, give me one sample calculation for the determination of your molarity. That's all I would need to see there. That would then get followed up with table 2, and that would be your equilibrium concentrations for each of the species involved. So you've got, I've already forgot them all. What were they all? You forgot them even faster than I did? We've got an ester in there. There's an alcohol, carboxylic acid, and water. I want the equilibrium concentrations for each of those, and then the equilibrium constant for each of those trials. Okay, that's just going to be trials 2 through 5. Why not 1 and 1A? There's no equilibrium reaction occurring in those two, so you don't need to summarize those results. After that, I would expect the calculations and an ICE table for trial number 5 and trial number 5 alone. You can give me the calculations for every other experiment. I'm fine with that. I'm just not going to look at them. Okay? Trial 5 is the only one I want to see. Okay? The reason being is trial 5 is the most difficult calculation because it involves more pieces than any of the others. So if you can do all the calculations right in trial 5, I will assume, which is potentially dangerous, that you can then translate those calculations correctly back to your other trials. Okay? The one case where you'll get in trouble with that is if your equilibrium constants don't come out relatively similar to each other. Then I will ask to see your calculations for trials 2, 3, and 4. Okay? If they all come out the same, we don't need to worry about that. Okay? Questions about what we expect to see there? Okay. Don't look too excited there. You're making me nervous. Okay, trial 5. The lab procedure kind of gave you a general format for your ICE chart. So they've set it up in units of moles. Why do they use moles and not molarity? I don't particularly like that they did that, by the way. Because what do we tell you goes as far as units into an ICE chart? Molarity. Always molarity. So why do we get away with moles here? Nope. To calculate the molarity, you would take your moles and divide by the total volume, right? Okay. So for our alcohol, we would divide by whatever our total volume is. So let's say 1 over 2. The acid, divide by 2. The ester, divide by 2. Water, divide by 2. 2 milliliters being our total volume. What's a half times a half? Quarter. What's a quarter divided by a quarter? Quarter divided by a quarter? 1. Why can we get away with moles? Our volumes cancel out of the equilibrium expression. That is the only reason we don't have to use molarity. Okay? So they decided to use a pseudo-simplification and then not explain why they did that simplification. It is up to you what you want to use. If you want to put moles in for everything, I'm fine with that. If you want to do molarity for everything, I'm fine with that as well. Just make sure whatever you decide, you are consistent with your application, be it moles or molarity. Yes?
Sorry, can you, so all of the volume, or is it, I'm sorry, I got a little lost on why we can use the moles instead of molarity.
To solve for your equilibrium constant, what do? It's products over reactants. How many products are there? 2. Since to get our molarity, we'd have to do by our total volume. The total volume for the alcohol is the same as the total volume for the acid. Okay, so in this case, I said the total volume was 2. So half over a half, or half times a half. Down here, half times a half, the mole or our volume ends up canceling out of the calculation. So it's not something that hurts to have in there. It changes your number, but when you go through to calculate your equilibrium constant, it balances out. We don't have to worry about it.
And why do we include water here, whereas in lecture we always never?
We don't include it in lecture because we include the water term as part of our K expression, because we assume it stays relatively constant. Here it changes slightly, and it's enough that it contributes to our equilibrium constant that we want to include it in our calculation. Otherwise, we're not solving directly for the equilibrium constant for this reaction. We'd be solving for it for the one that includes water in our equilibrium expression. So it's just a different frame of reference on how you're determining it. Okay. Other questions? Okay. What I'm going to attempt to do is go through some of the calculations here. And I'm going to keep it relatively short because I know some of them are going to bite me in the butt because I'm sure I'm going to do something wrong. Okay. So this is our ice chart. Come on, erase. What are you doing? So we've got our relative ice chart. I would kind of lean towards using moles as far as your ice chart goes instead of using molarity, because a lot of the calculations are going to involve you having to be in moles. So you're going to end up converting to moles. To convert it back to molarity is just an extra calculation that's not super necessary and is easy to mess that calculation up. So I would recommend you stick with the mole calculation. Okay. So to start off with, they went through and identified some variables within the ice chart. We get A, B, C, and X. To determine our equilibrium constant, what we need to know is this bottom row, just those values. Okay? So we need to know what A, B, and X are for every single trial. Okay? Some of them are easier to solve for than others. For instance, A. Let's try and figure out our A value. Since I decided that we're going to use moles in this case, we'll pick the moles for our ester. That's what we need to know. How would we determine the moles of our ester? What do we know about the moles of our ester?
Given the molar mass and the volume.
We know the molar mass and we know the volume. We also know its density, which is going to be the more important one here in a second. So we could start with the volume. We have 2 milliliters, okay, of our ester. Well, if I want to get to moles, we could look for a mole to milliliter relationship, which would be a molarity. Do we have a molarity for our ester? No. Kind of. So what do we have? Is there a relationship between the volume of our ester and something else? We know the molar mass. Okay? So what we would do is look up our molar mass of our ester. Whoops. Sorry. Molar mass doesn't work. Why does molar mass not work? Molar mass relates grams and moles. We have volume. We have the density. There we go. Density relates mass, mass to volume. Where did you get that number? That number came off of your bottle or your burette. You should have written that number down. If you didn't, good luck with the calculations. Okay? That means going to the stockroom and hopefully being able to tell them enough information about which row you used to be able to figure out what it was. Okay? That now gets us into grams. We want moles. What do we do? Is there a relationship between grams and moles? Now we can use the molar mass. Where did we get this information? also from the bottle. Okay. Symbol for density is that little rho symbol. Okay. We now know the moles of our ester. If we want to convert to molarity, we can. To do that, we would need to divide by, so I'll put this as an extra calculation. Divide by our total volume. Our total volume is going to be the sum of everything we've added in there for that trial. I can calculate it. We've got 2, 4, 10 milliliters. We'd have to make sure that we did the proper calculation or a proper conversion to make sure that we got that into units for molarity. So we'd actually have to do an extra calculation there. Whoops. 1,000 milliliters, 1 liter. Okay. If you want to take it to molarity. If you don't want to take it to molarity, ignore that last step. You don't need to do it. Okay? Because you're going to end up doing that calculation for every single one of these. So that gives us our value for A. So that's nice. Step 1. That was pretty straightforward. I like that one. So let's pick another easy one. How about C? C is our moles of our alcohol. What do we know about our alcohol? And volume. So for our alcohol, we added 1 milliliter of the alcohol times, we can go through and do our density relationship. Why is it not writing? There's too many H's in there. This would be again off the bottle for the alcohol. There's our density. Moles of our alcohol over grams, molecular weight, which again we got off our bottle. And then again, if we wanted to, we could go through and do our molarity conversion. Okay. So those two aren't too bad. The exact same calculation, we just change our numbers around. Okay. Let's pick another one. Which one do we want to solve for next? B or X? Because we got to solve for A, B, C, and X. We've got A and C. Okay, I guess I can deal with X. This is where the calculations get hairy. X. X is supposed to be the moles of our carboxylic acid. What do we know the acid reacted with? The base. Okay, well, what do we know about the base that we added? We know the volume and we know its molarity. So we actually can determine the moles of base added. Okay, so that's kind of nice. Would that be equal to the moles of our carboxylic acid? Seems reasonable. We add base, it reacts with the acid. Is the carboxylic acid the only acid present? No. We also have the HCl. So we don't get a 1-for-1 relationship back to our base. So if we go through and determine the moles of base, let's try this. Our moles of base will be equal to the moles of HCl present plus the moles of our carboxylic acid. Okay. So we can determine, man. Choking spit. Our mole, yeah, I knew you wanted to know that. I just wanted to share. What do we know about getting our moles of base? How do we do that? The molarity and our volume, so it'll be the volume added times the molarity, which our molarity should be darn close to 0.7 molar. Okay, we'll probably have to throw in a unit conversion there too. 1,000 milliliters. Whoops. Except I did it backwards. Okay. So we can determine the moles of base, but our next issue is that what we want, don't do that, that's mean. We want just this term. This is our x value. So before we can solve for the x, we also need to know the moles of base, the moles of acid present. So how do we determine the moles of acid present? Do we know anything about the acid that we added? Yes, but we don't even have to get into the weight yet. We're going to titrate solutions 1 and 1A. Why would we titrate those two solutions? We're going to add base to solutions 1 and 1A. What is that base going to react with? The acid that's present. What does that allow us to determine? The moles of acid present. So we can determine the molarity of the acid in that solution. We know the volume of acid added from our initial thing, which was 5 milliliters. We'll be able to determine our molarity based on trials 1 and 1A, which should come out close to 3 moles per liter. Okay, that squiggle was a bad idea. We now know the moles of HCl present. The last thing that we don't have would be x. We can now solve for what our x value is. See, simple, right? Okay, so to do that calculation, okay, our moles of acid, let's pull this out a little bit. The moles, we're going to have to be very, very careful with what we're referring to. It's not so much the moles of acid, but the moles of HCl. The moles of HCl in each trial will come from trials 1 and 1A. You will use those two trials to determine the molarity of HCl in those trials. That you can then use as your number down here, which I'm now highlighting in purple. We'll box in. That gives us the moles of acid. Once we know, the moles of HCl. Once we know the moles of HCl, we can then relate that back to the moles of base to determine what our X value is. Okay? It's a lot of back and forth. When we determine the molarity, we will be determining it for 2 trials. So what should we do from those 2 trials? Average, right? Average the... There's got to be a fly or something back there. Average the molarity determined from 1 and 1A. Once you've got that, you can solve for x. How happy are you with all these calculations? Really, it's coming down to, should I go through and calculate the water now or leave that for Thursday? Any questions about this? Because so far all we've covered A, C, and X. We need to know B before we can determine our equilibrium concentrations from that chart. B, right? Yeah.
I would just do it so it doesn't turn up on another video.
Okay. I will go through and try and do B. We're now out of space, which means I have to erase everything. But before I erase everything, are there any questions about what's up there? Definitely saw some squinting. Is there something you can't read that I can help with?
Yeah, I don't have my contacts in, so.
Oh, if that's all. It's not a lot I can help with on that then probably. Okay. Okay. I will try, because I know that coloration is not, or being able to match these isn't going to be super easy. A was our ester, which I'm attempting to color code. B was our alcohol. Sorry, C was our alcohol, I can read, which was orange. To determine X, I had that as a black color. Unfortunately, to get X, we also had to use purple. I don't know why that means plus and an arrow, but it does. Okay. And for that matter, blue. Blue's in there as well. So you can try and track back where each of these color references were coming from. I know, isn't that fun? Okay. We will attempt on Thursday to probably go through some of it again. But probably what I'll do is help each group individually with their calculations if they so feel. You don't want help with your calculations, good luck. Okay? So, last thing we'll go through and do was B, right? So let's clear everything out of the way. Let's start again. What color do you guys like the best? Purple. There we go. A new purple. Okay, to get our water moles. Okay. Where did our moles of water come from? So now what we've got to do is track where the water came in. How did water get into our reaction? What's that? I can kind of accept that. I want a little bit more than just that it's a reactant.
Measured it, put it in there.
We directly added water. That was one of the things we added. Okay? So this is going to seem a bit silly, but our moles of water will equal the moles of water that we added. Okay? Was there another source of water?
When we clean out the bottles.
No, we're assuming that that water contribution doesn't affect the equilibrium because it's right when we titrate, so we don't have to worry about it.
The DI
No, not the deionized water.
water in NaOH.
Nope, not the water in the NaOH, but getting closer.
The water that's created in F9 water.
That would be our X. Okay, that would be our change in X. So we don't have to worry about that. We've already calculated that. How else did water get in there initially? The HCl solution that we added had water in it. It wasn't just HCl. Okay, we added water. So we also have, and sorry, this is where I'm going to have to switch colors, the moles of water from our HCl. Okay, so we've got to determine both of those things to add this up and figure it out. Before we go through and deal with the moles of water from our HCl, can we figure out our moles of water added? How do we do that? What do we know about it? And more importantly, I was going to stick with our volume. Our volume for our water added was what, 2 milliliters? You brought up a very good point. We also know its density. How do we know the density? Because you could look it up or you could just say it's 1. I'm fine with that. Okay, so now we've got its grams. How do we convert grams to moles? We use the molecular weight of water. How do we figure out the molecular weight of water? Okay, there were 2 answers to that. Look it up, I did not like. Periodic table I liked a little bit better. We could use the periodic table to figure out the molecular weight. Where have we seen this calculation? It's the exact calculation we used to determine A and C. Okay? We used our density and we used the molecular weight to determine the moles. Okay? We could tack on the molarity calculation if you wanted. Again, that's optional, up to you. Okay? I'm not going to include it on this one. To get our moles from our HCl, that's a little bit trickier. Okay. What do we know about our HCl?
Concentration.
Okay, it's 3 molar, so we know its concentration. We know that because we did the titration and we calculated it. What else? This is the one I'm not sure I can organize super well. So if you thought the rest was a mess, sorry, this is only going to get worse. What else do we know about the HCl? We know how much of it we added. Okay. And we do know its density. So what we could go through and do is say that we've got, how much did we add of the 5 milliliters? So we took 5 milliliters of our HCl solution, and we know its density. Why am I blinking? I don't know why. Right? And this would give us the mass of the HCl solution. Okay, well, if we know the mass, couldn't we get that to moles? Using the molarity, right? Except, what's the problem with that? This isn't the mass of water or the mass of HCl. This is the mass of water and HCl. We want just the contribution from water. How do we get the acid out of that? So this is now the mass of our solution. This came from trials 1 and 1A, densities. Kinda, sorta. What things contribute to the mass of that solution? What things contribute to your mass? Is it just your bones? It's the bones and fat and muscle and water and all that other stuff. What things contribute to the mass of the solution of HCl? What are the pieces that make it up? It's the mass of the acid that's present plus the mass of the water that's present. What we're trying to get out of that is our moles of water that's present. We need to know the mass of H2O in that solution. We now know the mass of the total solution. I need to get rid of the mass of HCl. How do I get rid of the mass of HCl? Somehow I need to get a gram value.
We do know the density of HCl.
We do know its density, but we already used that up here. That gets us the solution, not for the gas.
Molar mass with moles.
We do know the molarity of the HCl solution. We know there's 3 moles roughly in 1 liter. So I've been highlighting stuff in green that you have to determine. Do we know how much of the volume we added? Yeah? What was our volume for trial 5? If we did our unit conversion here, I now know the amount of moles in that solution. Can I convert moles to mass? How do we convert moles to mass? Times the molecular weight, which happens to be 36.46 grams per 1 mole. All of that put together gives me the mass of HCl. If I subtract that from the mass of the solution, what am I left with? The mass of the water. What did I want to do with the mass of the water? Figure out the moles of the water. I can now convert my mass of water from the HCl solution into moles of water. How? Using molar mass of water. Add that back to my initial term. I now know B. Awful. Yeah. If you followed that, good job. If you didn't follow that, hopefully it'll be easier when you have numbers to work with. Okay? Put all of that together. All we've now determined is A, B, C, and X. We haven't even determined our equilibrium concentrations. We can now solve for our equilibrium concentrations by doing all the subtractions. Once we've done all the subtractions, we can now solve for the equilibrium constant. Congratulations, you are 1/4 of the way done. Now you got to do it for the other 3 trials. Okay? Understand why I said roughly a page per calculation? Okay? A lot of the calculations will be repetitive. For instance, the moles of water from HCl. What's the volume difference between the individual trials for HCl?